You plug in a music CD, expecting nothing more than playback. And without any warning, your system quietly gains a hidden layer of control you never agreed to. No pop-up. No visible installation. No obvious malware behavior at first glance. Just a system that is no longer fully yours. Now tell me, if something like that can happen from something as normal as a music CD, how much control do you really have over what runs on your system? That is exactly how one of the most infamous rootkit incidents in cybersecurity history began, and it changed how the world looks at trusted software forever. Welcome to BlueHat Cybersec Academy. In this entry of the Malware Encyclopedia, we're breaking down the most famous rootkits ever created, what made them historically important, how they operated, and whether rootkits are still relevant in modern cybersecurity today. Now let's start with the first major case, and we'll call this section the Sony BMG rootkit story, because that's exactly where everything became controversial. The Sony BMG music entertainment rootkit scandal is often considered the moment the general public was forced to confront rootkit technology. The company distributed music CDs with copy protection software that secretly installed itself on Windows systems. But the real issue wasn't just installation, it was concealment. Once installed, the software hid its own files and processes using rootkit-like techniques, so users couldn't easily detect or remove it. Now let's break down what that actually meant in practice. Step by step. It modified system visibility rules. It concealed running processes and files. And it even created security vulnerabilities that other malware could exploit. From a technical perspective, it blurred the line between DRM and malware. And the backlash was immediate and severe, because it revealed something uncomfortable. Stealth mechanisms weren't just for attackers anymore. They were being used by legitimate corporations too. So let me ask you here, if trusted software can behave like stealth malware, what does trust even mean in computing? Now moving forward, let's talk about a much more aggressive and technically advanced evolution, the TDSS and Alureon family. The TDSS rootkit, also known as the Alureon rootkit, represents what we call a bootkit-level infection. Unlike user-mode malware, TDSS operated at a much lower level, often targeting the boot process or deeply embedding itself into system drivers. Now here's what made it especially dangerous, and I'll list it clearly as we analyze its behavior. It could intercept disk and network operations. It could hide malicious traffic from security tools. It could survive reboot cycles consistently, and it could even reinstall itself after partial removal. So this wasn't just hiding inside Windows. It was influencing how Windows interpreted reality. And for defenders, this became a critical lesson. File-level scanning alone is no longer enough. Now let's shift into something more economically driven, but equally dangerous, the ZeroAccess rootkit. The ZeroAccess rootkit took a very different path compared to earlier examples. Instead of focusing purely on stealth or espionage, it was heavily built around monetization, especially click fraud and malware delivery. Now let's break down its capabilities in a structured way, so you can clearly see how it operated. It used kernel-level manipulation for persistence. It relied on peer-to-peer command and control infrastructure. It hid malicious modules from system tools. And it downloaded additional malware payloads silently. Now what's important here is scale and design philosophy. ZeroAccess wasn't just a hidden infection, it was part of a revenue-generating machine. And because of its distributed peer-to-peer structure, even partial takedowns didn't fully eliminate it. This marked a shift in thinking. Rootkits were no longer just tools, they were becoming criminal platforms. Now let's move into something even larger in scale, the Necurs botnet. The Necurs botnet rootkit represents industrial-level evolution of rootkit technology. It became one of the largest botnets ever observed, used for massive spam campaigns and malware distribution networks. Now let's understand why it stood out so strongly in cybersecurity analysis. It had highly sophisticated persistence mechanisms. It supported modular malware loading capabilities. It enabled large-scale botnet coordination, and it maintained long-term stealth operation across millions of machines. And here's the key takeaway when you step back and look at it. Necurs wasn't just hiding malware on one system. It was coordinating malware across an entire global ecosystem. So at this stage, rootkits had evolved beyond system-level threats into infrastructure-level cybercrime operations. Now let's move into something completely different in motivation, but extremely important in impact. Stuxnet. The Stuxnet worm is widely known for industrial sabotage, but its rootkit components played a crucial role in its success. And this is where rootkits move beyond traditional cybersecurity boundaries. Stuxnet used stealth techniques to hide modified PLC behavior from monitoring systems. It masked changes in industrial control outputs. It intercepted and falsified sensor readings, and it maintained operational secrecy inside critical infrastructure environments. So this wasn't about stealing data or making money. It was about altering physical processes while making everything still look normal. And that made Stuxnet a turning point. Rootkits were no longer just cybersecurity tools. They became industrial and geopolitical instruments. Now let's bring the discussion into the present, into modern rootkit trends. Modern rootkits have shifted away from obvious file hiding and instead focus on blending into system architecture itself. So today, we see trends like boot-level and UEFI persistence mechanisms, driver-level stealth injection, firmware and hardware-adjacent persistence, fileless rootkit behavior in memory, and advanced hooking techniques integrated directly into legitimate system APIs. So instead of hiding files, modern rootkits increasingly focus on something more subtle and more dangerous, manipulating what the system believes is true while it is running. And that makes detection significantly harder for traditional security tools. Now let's answer the big question directly. Are rootkits still used today? The short answer is yes, but not in the way most people expect. Today, rootkits are less common in low-level commodity malware, but they are heavily used in targeted attacks and espionage operations. They are frequently embedded within advanced persistent threats, and they are often combined with loaders, stealers, and ransomware chains. So they haven't disappeared. They've simply moved upward in sophistication. In modern cyber operations, rootkits are rarely the main weapon. Instead, they act as stealth layers inside multi-stage attack systems designed for long-term access. Now let's bring everything together into a final insight, because this is the part that really matters. If you look at all these cases, from the Sony BMG controversy, to TDSS and Alureon, to ZeroAccess, to Necurs, and finally to Stuxnet, you start to see a consistent pattern. Rootkits evolved along a single axis: control without visibility. The more advanced they became, the less they relied on obvious malware behavior, and the more they focused on altering system perception itself. And that's the real danger, because once a system can be made to lie convincingly, detection stops being just a technical challenge. It becomes a trust problem. And in cybersecurity, trust is the first thing rootkits are designed to break. Now let's turn this into a quick challenge before we wrap up, and I want you to think like a security analyst here. First of all, the rootkits we discussed. Which one do you think had the biggest real-world impact, and why? Second, why do you think modern rootkits shifted toward firmware, boot-level, and persistence-based techniques instead of file-level hiding? And third, if a system can manipulate its own reporting, what should defenders rely on instead of the operating system itself? Drop your answers in the comments, because this is exactly how real-world threat thinking starts. And if you're following the Malware Encyclopedia, make sure you stay tuned for the next breakdown. If this helped you understand how rootkits evolved over time, consider liking the video, sharing it with someone learning cybersecurity, and subscribing so you don't miss the next deep dive. Because in cybersecurity, it's not just about what you can see, it's about whether you can trust anything you're seeing at all.